It's a great pleasure to congratulate the Bosscha Observatory with the 90th anniversary of its beautiful size refractor, with which so many excellent measurements of positions of visual binaries have been made in the past 90 years. Now today I would like to speak to you about another type of binaries, not visual binaries, which in general have orbital periods ranging from decades to centuries. I would like to speak of binaries with much shorter orbital periods ranging from hours to maybe a few months to a year or something like that. Binaries which produce very spectacular high energy phenomena. It has been found in the past 70 years that many of the spectacular and interesting astrophysical phenomena that we observe on the sky are related to these binaries with rather short orbital periods. And I would like to give you here a couple of examples and then later go into more detail about these phenomena. In this picture, I show you 6 examples of quite spectacular binary systems and which also give us very important information on fundamental physics. In the upper left picture, we see nova binaries. These have orbital periods typically of order a few hours, and they consist of a normal star together with a white dwarf. These binaries can suddenly become 10,000 to a million times brighter than the Sun, and that is due to an explosion of nuclear fusion that takes place on the white dwarf. Another type of explosions related to white dwarfs we see in the upper middle figure. Those are the type 1a supernovae. It has been realized in the past decades that these are due to white dwarfs in binary systems where now the entire white dwarf explodes thanks to the transfer of matter from a companion star. Companion can either be a normal star or it can be another white dwarf. Here the star becomes something like 10 to the 10 times brighter than the Sun for a couple of weeks. In the upper right picture, we see the microquasars. These have turned out to be black holes in binaries, and they eject jets of matter with relativistic velocities. And this matter, the black hole receives from a companion star, and part of that matter it swallows, and the other part it ejects in the form of these jets. In the lower left picture, you see the X-ray binaries. It was discovered in the early 70s that the brightest X-ray sources that we know in the sky are binaries consisting of a normal star and a neutron star or a black hole. And also in the same early 70s already were discovered double neutron stars, 2 neutron stars which move around each other in orbits of 6 hours, 5 hours, 2 hours. And we now know that these double neutron stars are later evolutionary phases of high mass X-ray binaries, which you see in the lower left picture. They are a later evolutionary phase. And in the last couple of years, the gravitational waves were discovered not only from merging double neutron stars, but from merging double black holes. So we now also know that double black holes do exist. And also it was discovered that these mergers of double neutron stars give rise to what we call gamma ray bursts. In this case, short gamma ray bursts. And gamma ray bursts are known to be the brightest explosions of energy in the entire universe. And so we now know they are due to binary systems. And for 4 of these discoveries of the last 25 years, physics Nobel Prizes have been awarded. For example, for the discovery of the X-ray binaries, the Physics Nobel Prize was awarded to Riccardo Giacconi. And for the discovery of the gravitational waves from merging double neutron stars and double black holes, last year, Kip Thorne, Rainer Weiss, and Barish were awarded the Physics Nobel Prize. So you see that binaries are extremely important for fundamental physics. And you know, of course, from your own work on visual binaries, that binaries are very fundamental because they are the only source we have for measuring masses of stars. I would now like to focus on a few examples, the gamma ray bursts and gravitational wave detection. Gamma ray bursts are huge bursts of energy in the form of gamma rays coming from distant objects in the universe. About 1 gamma ray burst happens per day from a random position on the sky, and you see in the map in the left part of this figure you see such a position in galactic coordinates. There are 2 types of gamma ray bursts, short ones which last no longer than about 2 seconds, and long ones with durations between 2 seconds and several minutes. They have very different characteristics, and so they must have different origins. Now, for the short ones, one has the idea that they may be related to the merger of double neutron stars. This shows this theoretical model for producing a short gamma ray burst. We have here 2 neutron stars which are moving around each other in a narrow orbit, and due to the losses of gravitational waves, which is a form of energy loss, the 2 stars spiral towards each other, and at a certain moment they merge together, and in this merger also matter is ejected with a very large velocity, close to the velocity of light, and it is this ejected relativistic matter which produces the gamma ray burst. When these 2 massive bodies, neutron stars, move around each other in an orbit, this causes disturbances in space which propagate with the velocity of light, and we call those gravitational waves. And when such a disturbance passes the Earth, then also space at the Earth moves a little bit, causes matter to move away from each other and closer to each other again. Very small motion, but possibly detectable. Antennas to measure these gravitational waves, and there are 2 of such antennas in the United States, one in the state of Washington and the other in the state of Louisiana. They have these enormously long arms of about 4 kilometers and a very small displacement of matter from one side with respect to the other side can be measured. Very small displacements can be measured due to the passing of a gravitational wave. And quite remarkably, just 3 years ago, for the first time, people succeeded in measuring really the arrival of gravitational waves on Earth. And the first burst of gravitational waves that was detected on the 14th of September in 2015 was due to the merger not of a double neutron star, but of a double black hole. 2 very massive black holes with 36 and 29 solar masses merged here, and the signal was detected in both antennas in the United States, both in the state of Washington, and it's the upper left picture, and in the state of Louisiana, the upper right picture. And the waves that were generated by this merger, the 2 black holes were moving around each other. You see that in the lowest picture there. when the waves arrived, the two black holes were moving around each other about 40 times per second, and at the moment of the merger, they moved around each other about 500 times per second. And in this merger, something like 3 solar masses was completely converted into gravitational wave energy, and that energy then reached the Earth on the 14th of September 2015. The distance of these double black holes who are merging here were 410 megaparsec, more than a billion light years away. In the subsequent few years, 5 more of these mergers of double black holes have been observed by these LIGO antennas. And here you see the 6 double black holes of which the mergers now have been detected by the LIGO antennas. And the merger of a double black hole, of course, produces itself another much bigger black hole, as you see in each of these cases. And in the left case, the first merger event produced a single black hole now of about 63 solar masses. And the last event of last year, August, which was also seen by Virgo, produced a single big black hole of about 48 solar masses. Fantastic thing is that thanks to these discoveries, we now do know that in the universe, at many places, there are close double black holes, something we never knew before. Already for more than 30 years, it was thought that the strongest gravitational wave bursts that we could observe were due to double neutron stars, because double black holes simply were not known. And as I had already mentioned, what was expected that the merger of a double neutron star will also produce a short gamma ray burst. And there was a third effect predicted because matter is ejected, very neutron-rich matter. When this matter comes in empty space, it turns out to be very radioactive, and this radioactive cloud of decaying matter, radioactive decay, produces a lot of energy. This heats the cloud, and it would appear as a red star, which people call a red nova. Amazingly, all these 3 predictions came out on 17 August last year when LIGO observed a special gravitational wave event which lasted very long, 30 seconds, much longer than the merger of a double black hole. And LIGO saw the signal brightest in Louisiana, but is also very well seen in the Washington antenna. And amazingly, very shortly after the merger event, the Fermi satellite, a gamma ray satellite of NASA, and Integral, a European gamma ray satellite, saw a short gamma ray burst about 2 seconds after the merger event. The merger event began with orbiting neutron stars orbiting each other about 30 times per second and ended at about 500 times per second, as one can see in the left picture. And amazingly, immediately after this, all kinds of telescopes were pointed to the position of the sky of the gamma ray burst, and people saw all kinds of other radiations, as you can see. One detected all kinds of radiations from radio waves to gamma rays. This Chandra X-ray telescope saw the source, and with optical telescopes, one almost immediately found a new star which appeared in a galaxy, an S0 galaxy, at a distance of 138 million light years from us. In the lower right-hand corner, you see 6 optical pictures, negatives, and at the dashes there is the star which suddenly appeared there, and that star had all the properties of a red nova, which is produced by the merger of a double neutron star. So all the predictions of the merger event of a double neutron star came out here was absolutely fantastic, this discovery, and this is absolutely fantastic breaks. Also, even a couple of weeks later, radio emission of this event was detected. Apparently, it took this cloud somewhat longer to also start producing radio waves. But what we see here of all these things of the last 3 years is that now we know there are double black holes, which we never knew before. We have seen the merger of double neutron stars. We have seen that they produce the gamma ray burst. It is absolutely fantastic what we all have seen here in the high energy field. And we see here that binaries really have come to the front stage of astrophysics. 4 Nobel Prizes for binaries already in the last 25 years. And also your binaries, the wide binaries, which you're studying with the Bosscha telescope, also remain very important because they produce the masses of stars which we all need in astrophysics. I would like to thank you very much for your attention.